Welcome to this session. Here are 3 problems for us to prove based on congruence. So we are given that A is congruent to B modulo M, C is congruent to D modulo M. Then we have to show that A plus C is congruent to B plus D modulo M, and A minus C is congruent to B minus D modulo M, and A times C is congruent to B D modulo M. So these proofs can be done if you understand definition of congruence modulo. So proof. So by definition, A is congruent to C to B modulo M means M divides A minus B. This from definition. And then also, M divides A minus B implies they exist an integer K, or let's say S, such that A minus B is the same as this M times S. And then do the same thing as saying A is equals to B plus MS, call it equation 1. So equation 1 is just from definition. And let's now interpret the second. Remember, we have been interpreting this first congruence modulo that was given in the problem. Now let's also interpret this. So C is congruent to D modulo M means that M divides C minus D. This is from definition. Also, M divides C minus D implies they exist an integer, let's call it T, such that C minus D is the same as MT. Call this then IE. We can make C the subject and say C is the same as D plus MT. So this is call it equation 2. So we have equation 1 and equation 2 from definition. So adding 1 and 2, we have remember we have 2 equations. So one is A equals to B plus MS. B is 2 is C equals to D plus MT. So when I say I'm adding, I'll have A plus C is equals to B plus D plus M S plus M T. And you see A plus C equals to B plus D, put in brackets. And then I can say this is M into S plus T. Because you see M is common, which is the same thing as saying A plus C is equals to B plus D, and then plus, say, M K1, where K1 is an integer. K1 is M plus S plus T. You see, S is an integer, T is an integer. So adding two integers, we also get an integer. But then this equation is the same thing as saying A plus C minus B plus D is equals to M K1. Which implies, since this is an integer, this is M, M divides A plus C minus B plus D. And if M divides the difference, then this means that A plus C is congruent to B plus D modulo M. And the first property is proved. Second one, number 2, we have to show that A minus C is congruent to B minus D modulo M. We'll do the same thing. By definition, A is congruent to B modulo M implies that M divides A minus B. This from definition, which implies there exists an integer, say S, such that A minus B is equals to MS. This is just still from definition of M dividing M minus B. So this means A is equals to B plus MS. We call it equation 1. Similarly, C is congruent to D modulo M implies M divides C minus D. And this implies there exists an integer, say T, such that C minus D is equals to MT, i.e. C equals to D plus MT. Then you call this one question 2. Now subtract 1 and 2. So 1 minus 2 will give us, so remember equation 1 is A equals to B plus MS, 2 is C equals to D plus MT. So subtracting means I'll have A minus C is equals to B plus MS minus D plus MT. So which is A minus C equals to B plus MS minus D minus MT, which is A minus C equals to B minus D plus MS minus MT, just collecting terms in M together. I can put brackets here, and then this other term, I write A minus C is equals to B minus D plus M into S minus T. Don't forget that S and T are integers. And you know from properties of integers that difference between two integers, we also get an integer. So if we let K2 to be S minus T, and then this still just be an integer. So we'll have A minus C is equals to B minus D plus M K2, i.e. A minus C, you subtract B minus D, you get M K2. Remember, K2 is an integer. When you say A minus C minus B minus D equals to M K2, it's just another way of saying that M divides this difference, which means M divides A minus C minus B minus D. If this is true, then it's the same meaning as A minus C is congruent to B minus D modulo M. So hence, proved. And lastly, we show that AC is congruent to BD modulo M. So we have to show this. So solution or proof. A is congruent to B modulo M implies M divides A minus B. This from definition. And this also implies they exist an integer, say S, such that A minus B is equals to MS, i.e. A is equals to B plus MS. We call it question 1. And then C is congruent to D modulo M implies that if you take M, you should divide C minus D, which also from definition of divide operation, they exist an integer, say T, such that C minus D is equals to MT, which has the same meaning as C is equals to D plus MT. Call this one equation 2. Now, what we do in this case, we multiply. So equation 1 times equation 2 will have A times C is equals to B plus MS times D plus MT. So AC equals to BD plus BMT plus MSD plus M squared ST. So we can write this one as AC equals to BD plus, common here, we factor out M, BT plus SD plus MST. Don't forget that A is an integer, B is an integer, S is an integer, T is an integer. So the product of B and T is an integer. The product S and D is an integer. Product M, S, and T is also an integer. So an integer plus an integer plus an integer is just another integer. So we can fix this one by say K3 to be BT plus SD plus MST. This is just be another integer. So we'll have AC equals to BD plus MK3, where K3 is this sum. And from this equation, we check BD to the left. So AC minus BD is nothing but MK3. But from definition, if AC minus BD is MK3, then this implies that M divides AC minus BD. And if M divides AC minus BD, then this implies that AC is congruent to BD modulo M. And then we rest our case. Thank you.